G'day Bifrosters. Moving along on our scattering journey, we come to scatter and volume. Isn't this pretty? I think it's very pretty. So this one, while still using the scatter points node, is just a little bit different than anything else we've done so far. So it quite literally scatters in a volume. And as you can see, and as we do, we'll go through this and give some examples. Whilst I go through everything, I'm not going to show you how to build it, I'll just show you how to use it, as is the way we've been doing this thing. So right here we have dummy inputs. Now the first thing you notice looking at dummy inputs is you can plug in a mesh, you can plug in a level set, and you can plug in a fog. So all three of these work to scatter in. At the moment we're scattering on a level set, and the dummy input is basically just a sphere. Go to mesh, you can see nothing changes. It converts the mesh to a level set inside the node and then does the scattering on that. But it also scatters on the fog volume, and this is going to look very different very quickly. I'll go through that in a minute, but just so you can see, this is still a mesh. It's still got gaps from the fractal noise field in the weights. It's still doing it right, it just doesn't look the same. So there's going to be a little bit of change you have to make here with the depth to get a better idea of a fog volume, like so. Okay, real quick, let's go through it. I've literally just really quickly demoed the level set and the mesh and the fog volume. So what are we doing with this depth thing? How does everything else work? Well, taking a quick look inside, as always there are notes for you to look at. It tells you what's going on here and here. There's the scatter node there, there's the culling, point display, all that kind of thing. Just fix that while we're in here. So literally it's taking a volume and scattering on it. And the weights, as usual, is, if I unplug this, we'll just get a sphere, and it looks like it's turned back into a float. Again, it's an interpreted scalar port, which means that you can plug anything float related in there, and the weights behave just like everything else has. So if I was to quite happily just stick in a float in there, and we do 0.5, and we just drop that in there, we've essentially said to each point you have a 50% chance of spawning anywhere. You can see there are still many points in there. Everybody's happy. We can have a look at how many points we have if you wish. Right now we are playing around with 32,000 points, and that's from 64,000 points, so that makes sense. If I change that to 0.1, we should have about 6,400 points. We do. Excellent, that's working. So I'm not sure I need to explain the scatter settings anymore. This is the fifth video in the series. But I'm going to anyway. We have our scatter mode, we can random blue noise, we can radius number densities like we always have, we can change our amount. And this is blisteringly fast. I'll take that off. So we're at 100,000 points now. See how quickly this is going. It starts to slow down after about 200,000 on my machine anyway. That's not what I wanted. And I can show you just how quickly this is performing by we'll plug in a fractal noise field. There we go. And let me just change, not the magnitude so much, let's just change the ratio of this field really quickly. You can see how responsive this is. Change our frequency. You can get some really good looking effects with this. This is working quite nicely. There you go. So we have, that's covered again, seed. So you can just change the random seed. Density weights and the culling, same deal. Transfer properties as per. Yeah, I don't think I really need to go through the scatter settings again because we've been through them 4 times. So I'll move straight into mesh to volume. These control how a mesh plugged in will be converted to a sign distance field and then scattered upon. So anything in this mesh to volume category, so all of the modes and everything, it's literally the same as a convert to volume node. So anything in here, there's a solid you're bringing in, what's the offset, etc, etc, etc. Let me just show you how this works with a different mesh. So I'll bring in this skull mesh here, which I guess should be around somewhere. There it is in the middle. You can see that. Let's just make that a bit bigger. Hide it, and we'll bring it into the graph by middle click and dragging. And let's just pop that in the input. So now you can see, if we take this off, there's our skull. You can see the points that are being scattered on it. So right now, we've got maybe just a little bit of an offset. So let's change our resolution mode to absolute and wait just a bit while it sorts its life out. There we go. That looks like it disappeared, but it literally didn't. So now you can see that we have a really nice packing of points into that mesh shape. You can do a lot with this, so I can increase those points. It's a little bit slower now that we've set our mesh to volume to absolute. And we are scattering rather a lot of points. That is slowing it down, quite a lot rather, but you get the idea. Just if I was to just hide that, you can see we've got quite a bit of faithful detail, to the point of you've even got this kind of thing happening. So that's a pretty good thing. Let's just drop the number of points we're scattering for a minute. Speed things up a wee bit maybe. I'll set that to 6400. There we go. Just so you can still see that how the depth works. So this is your display. So this is your point color. Let's change that. That gives us a better idea. So you can see, there's our point color, and this is the point color at the surface of the mesh when it's an SDF. When it's a fog volume, it's based on density. But the color you choose is the color at the surface of the volume. You've got, they could be points or disks or spheres or whatever you want. Back to disk, just so everybody's happy. Default point size is how big or small these points are. So I'm going to take this back to relative. So we've still got something that looks like a triceratops, but isn't quite as detailed. It is, however, an awfully lot faster. So you can see when I change the depth here, that it appears to be getting brighter or dimmer. What this is essentially doing is changing the depth at which the points fade to black in the center. This one, you do get a much better idea if you're looking at a lot of points in a sphere with some fractal noise on. So if you see here, this is literally changing the color based on the depth from the surface of the volume. So in this case, very, very, very low depth, like 1, means that the points will go to black very, very quickly. You end up with something like this. You could use it to build a planet. You could do all kinds of cool things with it. But as you increase this, you can see that the color gradiates across the depth. And this is just the depth from the surface. Obviously, if you go to -2, they're all going to be, or minus anything, or 0, oh, not 0, sorry, my bad. If you go to -1, we're just going to get the color that you put in. So something like that. There we go. But if we take this back above 0, you can see your depth working. And it does work for fog volume as well. But because fog volume is calculated a little differently, this is done a wee bit. This is done a different way. So if we take a look in here, first off we'll take a look at our input logic. So this is, first thing it does is it checks to see if it's a volume or not. That's where the mesh comes in, and this is where all the settings come in here we were looking at before, which is cool. And here it checks to see if there's a sign distance property. And if there's a sign distance property, if there's a voxel sign distance on the volume, it means it's an SDF. And then it just outputs both the new volume and whether this has a sign distance or not. If we follow that along to the point display, you can see has sign distance here is coming in. And this looks a bit like spaghetti soup, but we'll just follow the lines as we do. Has sign distance, it's this guy. It comes into this big if. So if it has sign distance, this one, this here is how the SDF is calculated, and this one is how the fog volume is calculated. And you can see we're sampling the volume here. The property we're sampling is voxel fog density rather than sign distance, which is why the depths are a little different. But that is basically it. It is literally take a volume and scatter some points in it, and all the cool effects you can do with it. Alright, so that's all the settings worked out. Let's go on to doing something with it. Now that we've had a quick look at how this works, let's do something with it. So what can we do with something that fills points in a volume? I've been thinking about it for a little while. I can think of several things that it would be quite good for, including scattering the start points for particle system, ready-made clumps for snow and sand, stuff like that. But what we'll do today is we'll just do a little bit of, I don't know, motion graphics, I guess you could call it. So I'm going to start off with a new graph. There we go. Let's just go to the outliner and we'll just hide that guy. And first thing I'm going to throw down is I'm just going to throw down a scattering volume, which I have already published. And let's stick with the sphere motif. So from here we'll go from mesh sphere, like this. Put that into there, and let's have a look at what that's outputting. Well, it's a pretty small sphere. It's pretty small spheres. So this is what we've got. We've got quite a lot of particles, 64,000 particles packed into that sphere. Not particles, sorry, 64,000 points packed into that sphere. Let's take that down to 6,000. It looks like a little bit more manageable. And of course we can expand the radius of our sphere, something like that. 10 seems pretty good. It's looking pretty nice as it is. Now, as I said before when I was going through the compound, the scatter and volume, when you plug a mesh into it, it converts to an SDF, or a sign distance field, which means you get all kinds of nice distance things for free. And we're going to take advantage of that. So let's throw down some fancies. So we'll get down the factor noise field. This is going to look a lot like what I was demonstrating before. We'll take this guy and we'll drop the frequency right down. This is where we can now start to chunk this up. 80,000. Sounds pretty good. Make the factor noise field, keep dropping that frequency until we've got some nice looking chunks. Just going to be something like that. We'll get our depth working, because the depth is what we're going to need, and we're going to do it a couple of ways. So here I have a pretty chunky sphere, really, which is pretty good. I mean, you know, there's a whole bunch of stuff we can do to it to make it change or smoother. I think something like that might be quite nice, but smoother. And you can see we've got all our depth information ready to go. What are we going to do with this? Well, let's throw down another one. Let's just grab all of this. And we'll make another one. So just to make things easier to differentiate, let's change that around. I'll turn that one on. And we're going to take this sphere and let's more than double the radius. So there we go. And of course, let's change the seed of this field so it's different. We have the same number of points being scattered. We will of course need to change our depth here. I'm going to get something like that going on. And here we have a volume within the volume and two different scatters on each. I'm going to go to the noise field and just drop the frequency on this outside one down quite a lot. So we've got something like that. Maybe even let's just drop the number of particles a little bit. Yeah, maybe not that much. Just a little bit as well. So first thing I want to do is I want to clear out a space on the inside of this. So you can see if I hide this guy, and I'll change the background color, you can see I've got particles going all the way into the center. And kind of what I'd like to do there is I'd like to cut a hole in that. I'd like to have that like a hollow shell around, because we're going to do some nice things with it. So what I'm going to do is I'm going to drop down a sphere field, and let's have a look at the info for a sphere field. Scalar field whose value at any position is the sign distance to the surface of a sphere. Values outside of the sphere are positive and values inside of it are negative. Great. That's pretty much what I want. Now these are all centered on the origin, as you can see. So we'll just leave it that way because that's going to make my life easier. So I'm just going to add a mask field here, and this makes things a little bit easier to deal with. This basically value is 1 where the input scalar field is positive. So on a sphere field, outside of the sphere is positive and 0 everywhere else. So this takes this, which will become basically a bunch of numbers depending on how close they are to the distance field, and turns it into a 0 to 1 proposition. So for example, if I now multiply this noise field, which is providing us with our nice chunks and everything, we multiply that with the mask field and then plug that in, and there we go. We've now cut a hole in the center, and we can change the radius of that hole simply by changing the radius of this field. So of course if we get up to 25 it's going to kill everything. But now, what we have, turn our other one back on, is we have a nice orbital ring of 2. We basically have a nice clear space in the middle for our main field to talk to this field. And because we know the numbers, let's just standardize that so we get a little bit better. This is killing everything out to a radius of 15. Now, this sphere that we're scattering into, the volume, is a radius of 25, which means if I come down to my depth and change that to something like 10, then, or 15, actually it's more like 15, isn't it? Then the points on the inside are going to be black at just the right place. And it also allows us to start choosing things. And the reason we're going to choose things is what I'm going to do is I'm going to randomly pick some points from this volume in the middle. And I'm going to draw strands from those volumes out to a random point in the outer ring. Well, kind of random. They're going to kind of be closest together. And the way I'm going to do that is I'm only going to make one random decision. I'm going to get some random points in here, and I'm going to connect them to the top level points here using the depth. So first things first, let's get our scatter and volume. Let's get our positions. Yeah, we'll get our positions. Actually, no, let's not. just connect this up to the output for a minute because I want to show you the properties. So if I go in here, you've got a property here called point adjusted depth, which lives on the points object. This is the depth of the first scatter, pretty much, I believe, from 0 to 1 across the depth of the scatter. So let's work that out. So let's go, okay, what I want to do is the first thing I'm going to do is get from this. I'll hide this watch point for a second. I'll hide the info anyway. And so, of course, we're going to need to get the property. Get the point adjusted depth, and that is a flit, an array of flits. So now we just do a less than. So let's say if this is less than 10. Find all in an array, sorry. And what we're going to do here is just find every time that value is true. So all of the points that are less than 10, we're going to get those from the array. So I'm just going to make a little point display object. And display those points. So we'll go here, we'll give it, so they've gone black, and we'll give them a bright green color. See, these are all of the points with the depth is less than 10. The adjusted depth is less than 10. I change that to 0.5. You can start to see what's going on. So this is a 0 to 1, and that means, of course, that I have used the wrong condition here. So what we actually want to do is greater than or equal to. That's going to show us all of them, but as we bring this up, so now I can, if I pretty much set this to like 0.99, that's probably a little too much. Yeah, let's go 0.98. I'm just getting 1 or 2. Let's bring it down till we've got some of just the furthest out ones. Something like that. We don't have very many points there, but that's okay. We don't need very many points. But what we're getting is the points that are the closest to the surface. As I decrease that, I'm getting more and more across the depth. So this is a really handy thing to use. And you can use it for a lot of stuff. But I'm going to set that down like something like that. So we've got a few points. We can change this later, but this is just to set it up. So this is pretty much, it's as good as a random because we're scattering. If we look at our scattering volume, we're scattering random. So this is just pretty much finding the ones closest to the surface, but they're still scattered randomly. So I'm quite happy with that. So I'll leave that there. And what I want to do, this is just a display node, we'll be getting rid of that. So I want to draw some strands between these points and some point that is the closest to them on this outer points object, which is here. Great. You know, there's such a thing as like sample closest in radius, sample points by radius, or get points in radius. There's also get closest point. The trouble with get closest point, of course, is if you look in the info, only mesh and strands objects are supported. Other geometry types will not give useful results. This is neither a strand nor a mesh. This is a point. So I'm going to introduce you to really quickly to just a node of my own that I've built already, but I'll take you through it so you can duplicate it, or you can just download it from my repository if you want. And that is get closest point by position. It comes in, it's something I've done, I need to fix it up a little bit because I've done it just a wee way ago, but it's basically a loop. It's a loop. You can see there's the current index there. So what it's looking for is something called a feature points loop and the feature points. So all that means is these are the points you're going to loop around, and these are the points you want to find the closest to. So we know those already. Those are those guys. And what we're going to do is we're going to loop around all of the points in our second volume, like this. So now that we've done that, let me show you how that works in there. It's really simple. It takes the two inputs that you're giving it, subtracts one from the other, gets the distance, which now becomes an array of distances, sorts that array, gets the first, which is the second member in the array, because what comes out at the 0 position is the point itself, but I'm not entirely sure. So let's play it safe, make that editable, so we can play with it and you can play with it. And we'll take this and we'll go, yeah, just give me the 0 point. So give me the point closest, the smallest number in the array. So we've sorted our array of distances into closest to furthest away. We've got the first one. And then we're going to find, in this array, we're going to find this value. So this is before we sort the array. That then gets us an indice, which we grab from our feature points here. Which, if you remember, all of these points, so it's finding whatever the closest distance is in this array here, and then it outputs that to closest point position, and it also gives you the index. So that's how that works. Let's plug it into another one of these, and these are also fairly easy to make. We'll make this one red, plug that in there, we'll take a quick look. So I have made a mistake. Well, I shouldn't have. I think perhaps I did. That's more like it. Sorry, I had them round the wrong way. So really, really quickly, what you're seeing here is the closest point to each of these points in this array. And now it's just a simple matter to construct a strand. Well, we'll need to loop through and do it one by one, or build a strand offset. Because I don't want to build a strand offset, I'm going to just do another for each loop. Yes, I am lazy. Very, very lazy. So we've got those looping in there. We'll need, keep our names straight, would be a good thing. Let's just take a quick look, and because what we should have is we've got 168 points there and 168 points there, so that's cool. They're all the same, which means very, very nicely we can set both of these to be the iteration target for the loop. Construct the strands. So what I'm going to do is just set that to fan in, and we go from the inner to the outer, output our strands, and let's write down a terminal, and let's see what we've got here. Something's not quite working, is it? That's a bit more like it. So you can see a lot of these share the same closest point, which is great, which is fine. I'm okay with it being like that. But we could change that if you guys wanted to as well. And the way we would change it is to go the other way. It would be to go from these points to these points. Not so much in the loop, but in the get closest point by position. But there you go. So now I've just got to turn off these guys. And you can see really quickly I've got some pretty cool stuff I could do. I can also go to closest point by position. Because this is a loop, I can put down a random value like this. And what I'm going to do is just say, look, First thing I need to do is the current index needs to be the seed, so it chooses a different one every time. And I'm going to say, well, instead of getting the closest point, 0, why don't we get a random point between 0 and 5? So the six closest points. We just need to make sure that we set these to long, so the output's a long, and we'll pop that into the index and see what happens. Of course, when I change it to a long, it reset itself, so let's change that to 5 again, and then you can see they start to spread out, and we can start to do this kind of thing as well, and this is just randomly choosing to the first 15 closest points. Now, if you wanted to turn these into curves or, I don't know, tubes and Arnold to do cool things with and slowly rotate one around the other and have them switch, we can do that too. That wouldn't be too difficult to do. That would just be a matter of making one of the shells rotate and the other one stay still, and then having this running on every frame so that it picks up the distance. We can also, if we wanted to, we can also go like, I don't want the really, really close one. But this is just to give you a really quick idea of the kind of stuff you can do with scatter and volume. This is obviously not a very practical example unless you were doing some very cool motion graphics or working on Foundation, because Foundation is full of particles. There's so many Houdini pops in there, it's insane. But this gives you a good idea. Possibly a more practical example would have involved something like particles, and we can go through that if you want. I'm quite happy to use these nodes and show you. In fact, I've been using them in other examples I've been working on to show you as well. But yeah, so that's pretty much how you can use scatter and volume to achieve something fairly cool fairly quickly. You may have noticed that I've already got one called scatter and volume example shape, which is the longer version of this. I'll turn that on instead. And then you're getting that kind of thing going on. It's exactly the same idea. It's just using things like Bezier curves and a gradient compound that I've come up with. Feel free, this is the example file for the Bifrost browser. So feel free to just open this and pull this apart. You can see that I've given it some instructions here, and you can see the same. Let's just get rid of our outliner and make that a bit bigger. You can see the same setup. Here's our two scatter and volumes, the inner volume and the outer volume. Get rid of these, annoy me because they just turn up every time I open the file. And here you've got the point adjusted depth, the greater than, the find all in an array, just like we did, and it gets the start points for us. And then here's your get closest point by position loop. And you can see I haven't put in the randoms this time. This one I am actually getting the third closest, just for giggles. But I can change that to the sixth closest too, and everything will change eventually. This one's a little heavier. There we go. Like that. Then there's your mixed strands loop. So that's for loop we did before. This is using a little Bezier compound, which is, I've also made up, which you can play with, and then out it goes to 10 rules, whereas our volumes are out here. So yeah, feel free to have a look at that, play around with that, and let's just go back to where we were. And yeah, I hope that gives you something to play with and play around with and have fun. Okay, I'll let you all go. Thank you very much.